Okay, welcome back. So we are working on continuous time dynamical systems. We define the steady state. Now, once you define the set of steady state in this way, so a typical element is x star, and you require f of x star to be equal to 0, then uniqueness question is basically about the elements in S. Okay? If the number of elements in S is just equal to 1, you have a unique steady state. Okay? If this is greater than or equal to 2, you have multiple steady states. Okay, more than one steady state. So, is that important? Well, yes, of course. It is hugely important because, mainly because depending on the study you are pursuing, depending on the research question you have, more than one steady state will tell you many different stories. Let me just give you an example. Imagine that you are studying a capital accumulation model, but production function is specified in this way, and there is this one particular variable, let's say one particular parameter, let's say theta, okay, some technology parameter, and then you have again n plus delta kt, let's say. All right. Now you may, if you draw kt dot as a function of kt, if you get just this, okay, you have one steady state, right? Right here. But you may have something like this as well. Now, how many steady states do you have? If this is 0, you have 3 steady states, right? K1, K2, K3. So K1 star, K2 star, and K3 star. And as you see, 1 is the lowest, the 1 is the highest, right? And there's some middle range value, K2 star. Would that be important? Well, yes, because suppose that theta is now larger, okay? Now what happened? If theta is larger, suppose that this function shifts, okay? So this is theta 0, this is theta 1 greater than theta 0. Now what happened? Well, you just now only one steady state, okay? So why would that theta be important? Now enrich this story by making theta an exogenous variable, okay? And suppose that theta changes exogenously through time, and suppose that theta, for instance, increases in this way, okay? Suppose that this is some initial value, this is some final value, theta bar, okay? And what would it be? Well, it could be anything, but you may imagine factor eliminating technical change, for instance. So some factors that are used, for instance, land, because of technological changes, production technology would eliminate land, okay, from the production process. Then perhaps because of this, there's no poverty. There's no longer poverty, but all countries go to the rich steady state, for instance, okay? So there could be many different stories. As we will go along, I will show you some examples. So multiplicity of steady state usually an important issue, especially for if you are using such dynamic models for constructing models of economic development, for instance, you would see the importance of such stuff, because in the real world we do observe different growth regimes, right? Different development regimes. Some countries remain poor, some countries become richer and richer. There are some fast-growing, late industrializers, etc. Now, finally, we have the stability issue, right? Now, let me continue with the example we just studied, okay? So this is KT, this is KT dot, and the original figure I had was something like that, right? So this is K1 star, this is K2 star, and this is K3 star. Now, what do you see here? Of course, this is 0. Now, here, if you at the steady state, right? If you are at the steady state, imagine that this is let's say that, okay? Now, this whole thing, let's denote this by GKT, right? Now, your system is KT equals KT dot equals GKT, right? Now, if you're at the steady state, if you're at one of these steady states, what happens? GK star, either K1 star, K2 star, they're the same. So this is 0. This means there is no change in KT, right? By definition. So this is true for all three, right? K2 star, K3 star. Now, if you are out of steady state, let's say you are here, or let's say you are here in this region, or let's say you are here, or let's say you are here. Okay? Now, in stability, you are concerning the behavior of the system of the steady states. Okay? Now, let's try to understand this with this example. So suppose you are here at some K hat. Now, at this level, as you see, K dot is positive, right? What does it mean? Well, if K dot is positive, K will grow. Again, here, K dot is still positive, so K will keep growing. Until when? Until it reaches the steady state, right? Until it reaches the steady state. What about here? Here, K dot is negative, right? So what will happen? K will decrease. Again, negative, decrease, decrease. Keep decreasing until when? Until it reaches the steady state. So how about this? So of course, in this region, this is true as well, right? Because K dot is negative, so K should decrease. Now here, what's going on? Again, K dot is positive, so it should increase. Again, here it is negative, right? Should decrease. So what do we see here? What's the pattern? The pattern is that if G of K is less than 0, okay, evaluated at the steady state, then this steady state is stable, right? Look at this. Let me draw it again. So what's going on here? Here, at K1 star, G prime evaluated at K1 star is less than 0. Here, at K3 star, G of K3 star is less than 0. So these are stable. Okay? Because we have convergence to these points if we are away. Same is true here. But how about this? K2 star. Well, here I have this dynamic. Why? Because G prime K2 star is positive. Okay? So K2 star is not stable. Okay? So again, this is KT, this is KT dot, and this is 0. All right? Now, in general, then, we are interested in this derivative, right? So if my system is xt dot f of xt, I'm interested in the behavior of this system, of this f function at the steady state. Now, if you have one steady state, you talk about global stability. Okay, in the global stability, you have one steady state and nothing else. So when you talk about stability, you talk about this function, okay, this derivative. If you have multiple equilibria, you can only talk about local stability. All right? Why? Because here you can talk about the stability of K1 star. Here you can talk about the stability of K2 star. Here you can talk about the stability of K3 star. Right? If you let's say initially you are here. Initially you are at, so suppose that K0 is equal to K1 star here. Okay? And for some reason, at some t, KT is different than K1 star. Okay? Then only in this case, only if this is true, you start asking about stability, right? Stability question is well defined only if you are out of the steady state. But then, if the deviation is here, you cannot talk about the stability of K1 star, right? Because now you can only think about the stability of K3 star. So if with more than one steady state, you talk about local stability, not global. Okay? So there are some theorems in the text, and there is this famous Lyapunov function. But I will not go into that detail. I will not pursue that approach. Instead, I will pursue a graphical approach. Okay? Phase diagrams. Now, what you see earlier is a phase diagram. So this is a phase diagram of a system like this. Okay. Now we want to do it for two variable systems. Okay, we want to do it for two variable systems. So I will be interested in graphs like this. Okay, then I will have, let's say, a particular function for x1 t dot equals 0. Okay, and I will have another function for x2 dot equals 0. Okay. Now, obviously, you have two steady states, right? One steady state is here, and another steady state is here. And then, how many regions I have? Well, there's one region here, right? So this is one region. This is another region. Okay. This one is another region. Okay. This one is another region. And this also is another region. Okay. So in each region, I'm interested in understanding the behavior of the system. Where does it go? Right? Where does it go? Here. Where does it go? And here. Where does it go? Okay? That's our task now. Because what we did here is basically this, right? I found the steady states, and then there are 1, 2, 3, 4 regions. In each of the 4 regions, I understood the behavior of the system. Okay, I will do the same for 2 variable systems. Okay, now let's look at an example. Let's say x1t dot is equal to x2t minus let's say x2t minus 9 x1t square. Okay, and then x2t dot equals 1 plus 3 over minus 1 plus 3 over x2t. Is there a steady state here? So how do we approach this? Let's think about it. So suppose that this is your f function, fx1t, x2t, and suppose that this is your g function, x1t, x2t in general, right? So how do I approach this problem? Well, first we're going to define the steady states, right? So is there a steady state? I just made this system up. Maybe there's no steady state. So I have x2 star equals 9 x1 star square, and I have 1 equals 3 divided by x2 star, right? So what do I have? x2 star is equal to 3. Then x1 star is equal to 3 divided by 9, right? And the square root of this. Is that correct? So this is the square root of 1 over 3. Okay. So how do you draw it? First of all, let me ask you, is there a unique steady state here? Let's think about it. I mean, according to the second equation, that's true, right? X2 is equal to 3. What about this? Is that correct? Are you there?
There is a unique solution, I think.
So is this correct? Or should I have something else? So how many values of x1 star satisfy these equations? Let me simplify it for you. I now have this. How do you define the steady state here? So the steady state is defined in this way. x1 star square is equal to 1 over 3. Now this is a quadratic equation, right? So there are two solutions. x1 star A, let's say, x1 star hat is equal to that, and x1 star tilde is equal to that. Oops. X1 star tilde minus square root of 3. Right? There's something in the chat? No. Okay. So how many steady states do you have?
There's a unique steady state, I guess.
So this is not correct. Unique or multiple? You think about it, I'm just coming in a second. Okay, people, what do you think?
Multiple steady state in
Yes.
X1.
Yes, because x1 takes two different values and still satisfy the system, right? Right? Yeah. So we can draw it. So I have x1 t dot equals 0. So this is what? I forgot. Okay, x2 equals 9. x2 equals 9 x1 square. And the other is x2 equals 3, right? So you have something like this. If this is x1, this is x2, you have that. Let me use a different color. You have that. Okay, this is x2 dot equals 0, right? and you have something like this. Okay, so this is x1 dot equal 0. Right? So where are the steady states? You have one steady state here, and you have another steady state here. This is minus 1 over that. This is plus 1 over that. Okay. Now the question is, how many regions are there?
I think
How many
have
regions?
2 regions.
2. I think it is more than 2. Let me show you one of them. This is one of the regions. This one. Okay.
Then
This
we
is
have
one of the
4
regions. Another region is this.
Oh, 5 regions.
Okay, another is there. Let me show you another one. This is also a region. Okay. Then this whole thing is a region. Right? And finally, you have this. So how many? 1, 2, 3, 4, 5 regions. Right? You have 5 regions. So what we want to do is to understand the behavior of the system in all of these regions. Okay, here, 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 and here. How do we do that? Well, here's what we're gonna do. So our system is again x1t equals x2t minus 9x1t squared. x2t dot equals minus 1 plus x2 3 divided by, is that correct? Yes, I think that's it. Now, what we want to do is to know this. In each of these regions, now understand one thing. If you are at this point in steady state, and if you are at this point, right, here and here, you have x1t dot equals 0, x2t dot equals 0. Okay, so if you are at these points, there's no change in the system. If you are not at these points, the system will move. Okay, the system will move. So we want to understand, for instance, in this point, okay, in this point, we want to understand the sign of x1t dot and the sign of x2t dot. Because if I know the signs, I know whether x1 decrease or increase, whether x2 decrease or increase. Right? So but how do I find the signs of these things? Well, I can use computer power, right? I can write these functions to a computer, so I can compute the signs of these things for each x1, x2 pair, right? Because there are x1, x2 pairs all over, right? So I can use x1, x2 pairs and calculate the signs. But this is impossible, right? Because we have infinite number of x1, x2 pairs. An infinite number of x1, x2 pairs. I cannot do that for an infinite number of times. So I have to find another way. Now here's the idea. I know, for instance, in this direction, right? When x2 increases, I know that at some point for any x1, at some point, which is exactly there, x2 dot is equal to 0, right? Again, for any x1, it could be here as well. For any x1 in this direction, when x2 increases, I know that there is a point where x2 dot is equal to 0. Okay, so I will use that knowledge. Similarly, on this direction, for some x2, on this direction, there is a particular point, which is here, where x1 dot is equal to 0. And then, similarly, there's a particular point for any x2, right? When x1 is going in this way, there's a particular point where x1 dot is equal to 0. So I'm going to use that information. Okay? How? I'm going to use that information in the following way. Let me clear this figure a bit. Okay. Let me also clear this space. All right. Now look at this derivative. If I take the derivative of x2t dot with respect to x2t, what am I looking at? I'm looking at this direction, right? x2t increases. And what is the effect of this on x2t dot? What is the effect? What's that derivative? The derivative is minus 3 times x2t to the minus 2, right? Right? Now, this is a squared term, so it is positive. And this is positive, and this is negative. So this is always negative, right? So what does it mean? If this derivative is always negative, in this direction, when x2t dot, so x2t increases, x2t dot always decreases, right? When this happens for any x1, okay, when this happens, x2t dot decreases. But I know it is exactly 0 here, right? It is exactly 0 here. So what happens? Something is constantly decreasing, and at some point it is 0. Something, which is x2t dot, is constantly decreasing, and at some point it is 0. So what do I know? I know that Before that, it is positive, and after that, it is negative, right? Before that, it must be positive. After that, it must be negative. So as you see, I learned the entire behavior of x2 t dot, right? Because this is true for the entire region above the blue curve, and this is true for the entire region below the blue curve. Okay? So that's key. Now I want to do something similar for this one. Okay? x1 dot t. But I have less than 2 minutes. I have actually around just a minute. So let me stop here. And if you have any questions, I can answer them right now. If something is not clear, it's a very simple trick, right? Because I know along these lines there are sometimes equal to 0, right? So I'm exploiting this. I'm exploiting this to understand the sign of x2 dot, the sign of x1 dot. If I know the signs, I know the direction of change. That is the idea. Okay, so it is 2:35 almost. So let's meet at 2:50. Okay,
Okay.
2:50. All right, I'm ending this right now. Bye-bye.